Hi, my name is Harlan. Welcome to the H Matricon Mechanical Engineering channel. Today, our topic will be calculating the overall heat transfer coefficients in building structures. We need the value of the overall heat transfer coefficient in a building structure so that we will be able to calculate the heat loss in a building, and therefore we will be able to properly size the heating, ventilating, and air conditioning equipment. So let's have a quick review of the basic principles. For instance, we have a wall here with a thickness of X, and the temperature on the inside during winter time is T sub 1, and the temperature of the wall on the outside will be T sub 2. And note that T sub 1 is greater than T sub 2. Hence, heat flows from the inside of the building to the outside. And the temperature difference here will be T sub 1 minus T sub 2. And dx will be the differential thickness of the wall. Q is the heat transfer rate. And from Fourier's law of heat conduction, we have the basic equation of Q per unit area is equal to negative K differential of temperature with respect to the thickness X. So integrating, we have Q over A will be equal to negative K T sub 2 minus T sub 1 over delta X, and simplifying and reorganizing, we have Q is equal to quantity T sub 1 minus T sub 2 all over delta X divided by K times A. So the value of K here will be the thermal conductivity of your wall. So heat flow is equal to thermal potential difference here, which is T sub 1 minus T sub 2, and the thermal resistance. So for a three-layered composite wall composing of three materials A, B, and C, we have T sub 1 in the inside of the building, and we have T sub 2, which is in between wall material A and B, and also T sub 3, which is in between the material B and C, and we have T sub 4, the outside surface of the wall, and then so we have the heat flow rate, Q, and of course we have this area. So for a three-layered wall consisting of the three materials A, B, and C, we have, since the heat flow rate divided by the area will be constant overall as it goes through the different materials A, B, and C. So the heat flow per area is always equal when it flows through A, B, and C. And rearranging the equation, we have Q is equal to quantities T sub 1 minus T sub 4 all over. We have the thermal resistance here, delta X sub A over K sub A, and delta X plus B, delta X sub B, and K sub B, A, plus delta X sub C, K sub C, A. Okay. And in terms of heat resistance, you can lay it out in this manner so that you will be able to understand clearly. This one will be the heat rate, Q, and then it's constant as it flows from A, B, and to A, B, and C. And then you have R sub A R sub B, and R sub C. So these resistances are in series, the heat resistance. So here, and if it consists of convection, let us now consider convection. We have the temperature of the air in the inside T sub I, and we have the same T sub 1 here, inside surface of the wall, T sub 4 outside surface of the wall, and we have T sub O will be the temperature of the air outside during winter time. So the heat flows in this manner. This will be the heat rate, the flow of the heat going here. And from Newton's law of cooling, you have Q over A will be equal to H quantity T sub W minus T sub alpha. And we have here, which H is the coefficient of heat convection, and TW is the temperature of the wall, and T alpha is the temperature of the air. So for the overall heat transfer, we have the heat rate per area will be equal to H sub I, quantity T sub I minus T sub 1 is equal to K sub A, quantity T sub 1 minus T sub 2 all over delta X sub A is also equal to K sub B, T sub 2 minus T sub 3 divided by delta X sub B is also equal to K sub C, quantity T3 minus T4 all over delta X sub C is also equal to H sub O, quantity T sub 4 minus T sub O. So rearranging, we get this equation. Q is equal to T sub I, which is the temperature in the inside of the inside air, minus T sub O, temperature of the outside air, all over the resistances, 1 over H sub I A plus delta X sub A over K sub A plus delta X sub B over K sub B plus delta X sub C, K sub C A plus 1 over H sub O, the outside air, over A times A. So this will be the resistance of heat transfer due to convection in the inside air, and this one will be the for the outside air, and this one for composite for the wall section A, and the wall section B, and for the wall section C. So heat flow is thermal potential difference divided by the total thermal resistance. Your overall heat transfer coefficient is capital U is equal to 1 all over the resistances 1 over H sub I plus delta X sub A all over K sub A plus delta X B K sub B plus delta X sub C K sub C plus 1 over H sub O. So you will have here, take note, the total resistance values. And you have Q, the heat rate will be equal to capital U, which is the overall heat transfer coefficient, times the area, times the quantity of T sub I minus T sub O. And so in terms of heat resistance, you can represent it in this manner. So let us go to the example. For instance, we have a brick wall, which is constructed as shown below. And we need to calculate the overall heat transfer coefficient. Note that this one is an 8-inch brick wall made of fired clay. And this one here is a 1x3 wood vertical furring at 16 inches on center. And this will be your airspace. And we have here on the inside your 1/2 inch gypsum board. So to make it simpler, we will divide the wall section into two parts. The part at the furring and the part between the furring as shown below. So this will be at furring here, and this one here down between the furring. We can apply equation 11 to obtain the average coefficient heat transfer U sub average for the wall section as it is discussed in chapter 23 of the ASHRAE Handbook, Fundamentals of 2005, American Society of Heating, Refrigerating, and Air Conditioning Engineers, in the section entitled Series and Parallel Heat Flow Paths. In many installations, such as wood frame construction, heat flows in parallel paths of different conductances. U sub average will be equal to A times U sub F plus B times U sub B. So where U sub F is the coefficient of heat transfer at the furring, and U sub B is the coefficient of heat transfer between the furring. And A and B are the surface weighted path fractions for a typical basic cross-section. Take note that the actual dimensions of a nominal 1x3 is 3/4 by 2.5, so that the airspace between the furring is actually 3/4 inch. The following resistance values are taken from tables 1, 3, and 4, found in chapter 25 of ASHRAE Handbook, Fundamentals of 2005. For thatched walls at 16 inches on center, the framing factor is usually 25% of the wall area. So whereas the stud walls 24 inches on centers, the framing factor is 22%. So at the furring, when I first saw at the furring, so the inside surface having steel air, so we have the resistance will be 0.68, which is taken from table 1, and 1/2 gypsum wallboard is 0.45 taken from table 4, and the airspace, you neglect it. It's non-reflected airspace, and 1x3 vertical furring, 1.05 from table 4, and the 8-inch fired brick clay, and we have 1.6. Let us assume that it has a density of 100 pounds per cubic feet. And for the outside surface during winter time, we have, considering wind speed of 15 miles per hour, R will be equal to 0.17 from table 1. So then we add the resistances. We'll be able to take the value of R sub T of the furring, 3.95, get the reciprocal of this so that you will have the value of U at the furring, will be equal to 0.253. Now let us go to the calculation between the furring. Inside surface steel air, the same, 0.68 in table 1. 1/2 gypsum wallboard, the same, 0.45. Non-reflected airspace is 1.01 from table 3. And 1x3 vertical furring, we neglected because there is no furring actually. We are between the furring. So 8-inch brick, fired clay, 100 pounds per cubic feet density. We have R 1.6 from table 4. And outside surface, we assume wind velocity during winter time of 15 miles per hour. The resistance will be 0.17 as taken from table 1. And we get a total of these resistances to 3.91 and get the reciprocal so that you'll be able to determine the overall heat transfer coefficient for the portion between the furring. And we will be able to get 0.256. And so calculating the average heat transfer coefficient, we have from the formula, we have 0.25 times 0.253 BTU per hour square foot degree Fahrenheit plus 0.75 times plus 0.75 times 0.256 BTU per hour square foot degree Fahrenheit. So you will have the average overall heat transfer coefficient of 0.255 BTU per square feet per hour for square feet degree Fahrenheit. So another example, find the overall heat transfer coefficient for a flat roof assembly shown below. So here in the roof section, at the inside, we have a 3/4 metal lath and sand aggregate lightweight plaster. We have here the joist, which is actually a W section, W6 by 25. And we have here the metal deck. And above the metal deck, 3/8-inch built-up roofing. So again, the following resistance values are taken from tables 1, 3, and 4, found in Chapter 25 of ASHRAE Handbook, Fundamentals, American Society of Heating, Refrigerating, and Air Conditioning Engineers. Inside surface steel air, 0.61 from table 1, 3/4 metal lath, and lightweight sand aggregate plaster. We have the resistance value of 0.47 taken from table 4, and we have the joist, which is made of a steel section, so we have a 0 resistance. So, and then we have your non-reflected airspace, which is 0.93 taken from table 3, and the metal deck will be 0, and rigid roof deck insulation will be having C is 0.36. We have the resistance value of R equals 2.78 for 3/8-inch built-up roofing. The resistance will be R is equal to 0.33 from table 4, and the outside surface, as mentioned earlier, it's considering the winter wind speed velocity of 15 miles per hour, the resistance will be 0.17 taken from table 1. And then we get the total of these resistances. We have here the value of 5.29, and get the reciprocal. So your average will be 0.189. So calculating the average heat transfer coefficient, we have U average is equal to 1.189 BTU per hour square feet degree Fahrenheit. So that goes our discussion on the procedure for calculating the heat transfer coefficients for building structures. And I would like to invite you, if you were not able to subscribe yet to our channel, H. Machacon Mechanical Engineering channel, kindly press the subscribe button. And also, we would like to invite you to more video tutorials at our YouTube channel, H. Machacon Mechanical Engineering channel on YouTube. Thank you for listening.